And the book has, as I said, some other methods. So we'll do beam deflection using superposition. That is, if you want to find the deflection due to a complicated load, then you can break it down into uh, the sum of simpler loading conditions. And those loading conditions you can either derive using the equations I showed you in last class, or you can use the table. And we just use the tables to do it this way. Okay, so in this method, okay, and I'll make it clear when I say what I've said there about superposing. Now, there is some assumptions we make here, and those assumptions should hold true before we can use this method of superposition. So superposition holds as long as the following is true. One, so the deflection, or rather distortion, is in the elastic region. This means that it's not going to be plastically deformed, which happens when the loads are very high, which makes which doesn't really let us use the equation which we used for to find the beam deflection, which had the E, right? So second assumption is one load does not affect the others. There's one load will not cause an easiest way to check this is you put a load, you see the deflection. Well, you can put a load, see the deflection, and then add the second load and see the new deflection, and then you can reverse the way you apply the load, and in the end you should see that the deflections are the same. So that means that one load is not affecting the deflection due to other, and that's when the second assumption holds. And then the final one is that any load does not affect the geometrical relations of parts of the structural system. Which means that the loads are such that it doesn't lead to something like, some of the reactions changing in ways which changes the way these beams are deflected. So what we'll do is we could potentially derive these equations and use them, but the book has already done this for you. So we will use superposition plus A9 in the book. Okay, now what A9 does is it gives you slopes and deflections for common loading conditions and for different beams. So here is A9, which I plucked from the book. This is a beam subjected to a force. This is actually one of the problems I solved in the class last time, right? Load F at the end. So it gives you the shear force and the bending moment diagram. It also gives you the slope. It doesn't give you the deflection, but you can find the deflection by just taking the first derivative of y, and that's super easy, right? And then this is another case where the force is not at the tip, but at the middle. You can keep going on. Cantilever subjected to uniform load. That's number 4, moment load. Now we come to simply supported beams where the force F is exactly midway. Force is not midway. It's somewhere between A and C, which are the ends of the beam. Then we have uniform load, moment load. Okay, that's about it, I think. Oh no, there's another one. A few more, sorry, we are page 5. Okay, 2 loads and just so on. Okay, so what I would do is before I solve anything and try to derive equations, I would just look at this table to see if those meets one of those cases, and I can just pluck it from here and solve the problem. So let's see how to use this table in a few problems. Okay, so here's problem 1. Okay, so this beam is subjected to a distributed load first. Okay, and then there's a point load. Set a point C. And the distances are, the beam is 8 meters long. It should be slightly to the right. Okay, and then C is 2 meters from A, which is not shown. So we show that A is the left tip and B is the right tip. Okay, so the question is find the deflection and slope at C. Or compute the slope and deflection at C. You're given that E times I is 100 mega Newton meter square. Yeah, and I forgot to give you the load. So this load P is equal to 150 kilonewton, and the distributed load is 20 kilonewton per meter. Okay, so one way of solving this problem is to not use the table, just do what we did last time, which is you break it down into sections. So we have A to C, where C the load changes. So we draw a free body diagram from A to C, write the moment equation, M equals get the m, and then m equals ei d square y dx square. Integrate that for the left half, do that for the right half from c to b, and then you'll have, like previous, you'll have four constants which you need to find by using boundary conditions. So that's going to take a lot of time, and so we'll just make a shortcut using superposition and what we have from the table. So here is how it's done using this other method, which is using superposition. So here is how you do it. First, we identify that you can compose that loading in terms of two things. One is a point load P and a distributed load W of 20 kilonewton per meter. So I will find the deflections and slope due to those individual loads and then sum it up. That's pretty much what I'm going to do. So let's draw the beam with a point load of 1, or let's just put P, and then the beam with distributed load. So let's call that W. Okay, so we know that if you take the deflection, if you compose them together, then you will have the loading shown on top. Let's see, right? And so I'm just going to find the deflection at C on the left side, deflection at C on the right side, sum them up. Now, I could find the reaction forces, but that work has already been done for you. So let's try to go to the table and find where we can see this case. Okay, so go to the table. It should be in the beginning somewhere. Okay, it's not the cantilever. It's probably it's not this one either, because this is a load in the middle. It's this case, right? So we have R1, R2, the reaction forces. You can see that they've already solved them for you. You have R1, R2 already in the table. So you don't need to solve it. In fact, you don't need to even write that down because you really don't need it. You only need to know what the deflection is, YAB and YBC. In fact, we can use either of those formulas, YAB or YBC. We just have to be careful about how we substitute X. So let's use the YAB formula. So that gives the deflection from A to B. So I'll write that down, and then I'll put the values for A and B. So note that A is the distance from the left side, B is the distance from the right side, and X is the distance, I believe, from this point, right? From point A. A is the origin. So let me copy this down. So this is A9 number 6. So I'll refer to it as that. From A9 number 6, we can write down. So let's okay. So let's just call this C1 and just call this C2. They're the same things, but I just call them that so that way I can then sum them up. So YC1, that's now from the table, is FBX. So I just copy pasted the value from the table. 6EI times L X square plus B square minus L square. Okay, so you got to believe me that I copied the right thing. Once I got that, I can find the slope. That would be dy by dx. So now, you know what? Let me just write it as y. And then when I substitute, I'll put C1. So dy by dx equals, so I just take the derivative of this whole thing. So what I can do here is, to make my life easy, I can move this x inside. So I'll have x cubed, and so the derivative of x cubed is 3x squared, and then I'll have b squared times x. So the derivative of b squared times x is just b squared, and then similarly minus L squared. Okay, so I skipped a step there, okay? Other b, okay.
That's supposed to be like stress or a 6.
Oh.
Like the denominator.
it's 6. Yeah, my B looks like my 6. It looks like, my God, my 6 looks like my B, and my B looks like a 6 also looks like sigma. It's 6.
Wait, so that's a B on the top?
Yes.
Okay.
Is there an L at the bottom?
Yeah, I understand. Okay, so what remains is I need to identify what these quantities are, right? These are from the table. So I just copy pasted them. Let me write down what was X again? X was the distance from the left side. X, Y, let's see for this. Okay, so let's just start identifying these things. So from that table, from that, you should really have it close to you to see it. So F is P, which is 150 times 10 raised to 3. And then again, reminding you, A is the distance from the left side, B is the distance from the right side, and L is the total length. So what I can do is I can write those values here. So F is that. Let's write A, which is 2. It's the distance from the left side, A. B is the distance from the right side. So we have 8 minus 2 is 6. So I was looking at this. And then L is the length, which is here. It's 8. Okay, now since I need to find the deflection at C, I need to put X equals the distance from the origin to C, or C1. So X will be 2. And then EI is given to us. It's 100 times 10 raised to 6. Okay, I believe I have everything in there to go ahead and sub it. So Y at C1 equals, so when you put the values, you get this answer, 0, 0, 9 meters. And then dy by dx at C1 is minus 0.003 radians, right? It has dimensions of radians.
Is that like a 4 or a C1 or what?
C1. C1. Okay, let's now go back to the table and see if we can figure out what the deflection for the right hand side is, for the right loading is. So go back to the table. Okay, it looks like it's like this one, right? The uniform distributed load. Again, you're given the reaction forces if you want them. You're given Y. So let's take that Y, Wx divided by 24 EI and so on. So I'm going to take that and write it down first, and then I will sub in. So in this case, A97 Y equals W times X divided by 24 EI. It's 2L X squared minus X cube minus L cube. Can check it quickly. It looks right. Okay, so define dy by dx. Again, so easiest way to do that is to move that inside. If you don't do that, you have to use the chain rule, but easiest is to just move that inside. So what I would have is, let me write down the first constant term. So I would have 2L times x cubed because I moved the x inside. So that the derivative of that is 6LX squared minus, when the x multiplies with x cube, I have x raised to 4. So 4x cubed minus L cubed times x. The derivative of that is the cube. Okay, what remains now is to sub in the values for the various constants. So here we have W, which is 20 times 10 raised to 3. The length L is 8. X is the distance from the point A. It is going to be 2 meters for C2, so 2. And then EI, like previously, it's 10 times 10 raised to 6. Okay, so Y at C2, after plugging in the values, we have minus 0.076, and dy by dx at C2 is minus 0.029. Okay, so the final step is to find the combined deflection at C. So Y at C, which will be YC1 plus YC2. So I just take YC1 and YC2 and sum them up. It comes out to be minus 0.0166 meters, which is equal to minus 16.6 millimeters. Yeah, you wouldn't expect the deflection to be too much, right? It's about 1.6 centimeters, very tiny. And then dy by dx at C equals dy by dx at C1 plus dy by dx at C2. So just sum them up and you get minus 0.0059 meters. Okay, so that was probably a straightforward problem where it was like everything was pretty much there in the table. Here is a slightly more involved problem because this. So the next question is the cantilever problem. Okay, so that's the loading. It's only 1/2 of the cantilever. So the question is find the slope and deflection at point B. Is this? So here you're not given numeric values for L or W. You need to solve in terms of W, L. So solve in terms of W, L, and E times I. So the first thing we want to ask ourselves is, how can we do this with superposition? How can we break it down into multiple cases, right? So let's look at the table and look at all the cantilever solutions we have from the table. So go there. Okay, so this is one where the entire cantilever is loaded with distributed load W. This one, well, I missed one. So that's a concentrated load, doesn't help. This is a load in the middle, doesn't help. This might help a little bit because there's a load W. This one doesn't have distributed load, so we can't do 4. 5 is different case, not cantilever. 6 is a different case, simply supported. 7 is also simply supported, not a cantilever. Same for 8, simply supports. Missing something here. Yeah, simply support, simply support. You can just read it off from the wording here. 1 fixed, 1 simple support. That doesn't satisfy us. 1 fixed and 1 simple support. Nope. Okay, so 1 fixed and 1 simple support. It doesn't look like there's any more cantilever only. So that fixed supports both sides. This is the last page. And then we have fixed supports on both sides, fixed supports and uniform. So there's pretty much only one case which relates to what we're doing here. This is number 3. Okay, so there's that case which you can potentially use. Okay, so how do we use this case? Well, what we can do is this. We can think of, so first just put the case which you know about, right? So just put a load W, the whole beam, right? Now the question is, we know the solution for this one from the table, but what other case can we solve such that the sum of this case, one which I showed you, plus something else gives you this loading? And you can see that if you do it this way, you take this load W and you put it downwards over a distance of L divided by 2, right? Then you would recover the original case, which is a load from midway all the way to the end B. Okay, so my goal is to solve for these two cases and then add them up to get the answer to the problem. Okay, so how do we do this? Well, this case is already given in the book, right? So we know what the deflection is. It's right here. So I'm going to copy this down. So from A9 number 2 or number 3, sorry, we can write down the deflection as W divided by 24 di 4 times L x cubed minus x raised to 4 minus 6 L square x square. Okay, so if you take the derivative of that, it's so derivative of x cube is 3x squared, so 12x squared minus 4x cube minus 12L square x. Okay, so in this case, I need to find the deflection at B. So all I need to do is put the value for x. And like the previous case, my origin is on the left side, so at A. So y x, y x. So at P, x will be L. And so y at B, let me call that B1, just to indicate that this is the deflection due to case 1, is comes out to be negative as expected, because it's positive is upwards. So it's minus W L raised to 4 divided by 8 EI. And then the deflection is, again, if you put x equals L in the second expression, you get 20 W minus WL cube divided by 6 EI. Okay, so that was fairly easy. Now, how do we solve for the second case? So the second case, the issue is that there's no such loading in the book, like having a W divided by 2 on the left side and no loading. So what we can do here is we can still use the same formulas which we have for this one, but we just treat this like a beam of length L divided by 2, right? So when this deflects, in this case, it's going to deflect upward. So you would have something like this. Due to the load. So what we need to do is we can find the deflection So let's call that deflection as, so this is, let's call this point C. So the deflection here adds, and let's call it C2. Let's call that B2. So we can find the deflection here, and then we can find the slope here. Okay. And then if you want to find the slope and deflection here at B2, then what happens here is that the slope is the same. So this, from this point to this point, so I didn't draw it quite right. So it's going to be bent in a curve up till here, till the loading. And then it's going to be something like this. So the slope here is going to be the same as the slope at C2. So this will be the same. And that's because from C2 to B2, it's going to be, there's no load, so it's going to have the same slope. The deflection won't be anything new because there's no load acting between C2 and B2. However, if you want to find deflection at B2, it will not be the same as C2. You can see clearly that. Let me draw this again. Okay, I'm not going to show the load. So we saw that this is YC2. Now I need to find what YB2 is. Okay, so what I'm going to do is I'm going to use the fact that I know the slope here, which is dy by dx at C2. And then you can see that YB2 will be this YC2 plus this part, right? And that part is given by L divided by 2 times the slope. So this is basically trigonometry. When you have, when you're given L divided by 2, you're given this side, you're given this theta, then this distance is L by 2 sine theta, right? But since theta is small, we can approximate this to be L by 2 times theta. And that theta is dy by dx. Small angle approximation. Anyway, so this is my formula for YB2, and this is my formula for, again, for y dy by dx B2. It's good, same as dy by dx at C2. Okay, so since we've got this down, I'm going to just write the expressions down and then get this value. So let's just do that. Okay, so again here we would have, we'll use the same formula. Okay. So let's call that 1 and 2. Okay, so what we need to do is in 1, okay, then in 1, okay, we can do both, I think, 1 and 2. We'll put here the length is now going to be the half length, right? Because the loading is only for the first half from A. So L will be substituted as capital L divided by 2. And then you see that the loading in this case is downwards. That's why we wrote positive W. So here the loading is going to be in the opposite direction. If I don't have that, then I won't quite get the right answer. So I need to put W equals minus W. And then for X, if I want to find the slope at B2, I just need to find the slope at C2. So I need to put X equals L divided by 2. So get the slope at C2, which will give me the slope at B2. And same over here, I need to find C2 first, and then I need to compute the slope to get YB2. So what I'll do is I'll put X equals L divided by 2. Okay, so subbing in the values, I get Y at C2 equals, sorry, let me write the dy by dx first. So it's WL cube divided by 48 ER. And we have y at C2 equals WL raised to 4 divided by 128 ER. Okay, so this comes from these substitutions, and I just solved for slopes and deflection at C2. Okay, note the sign is positive because it's going to go upwards. Okay, so then if I want to find dy by dx at B2, it's going to be the same as dy by dx at C2. So that's the same answer. And then if I want to find y B2, it will be y C2 plus dy by dx at C2 times L divided by 2. So if I do the math on this, it comes out to be
So why C2? Like,
this one.
Yeah.
C2. Have some more space. So that comes out to be 7 times WL raised to 4 divided by 384 ER. Okay, so I'm not done yet. I just found the deflection due to case 2. This is all case. This is a continuation. Okay, so the left half is simple. The right half is all, which is a lot of work because of the special case it is. Okay, so we're done with that. Now we need to put that together. That is the principle of superposition. I need to find what the net deflection and slope is. So what I'll do is I'll sum it up, essentially. Sum, we call that this piece is A, and then we can call this piece as B. And so I just want to sum the A and B together. So the net deflection at B is the deflection at B1 plus deflection at B2. So the summing it up gives me, just put this down in case it's less clear, plus 384 41. Yeah. Okay, and then okay, those are my final answers.